In this session, we're going to cover joint PMFs and PDFs. So you could have a situation in which there are two discrete random variables, let's say x and y. So you have a PMF for x, which tells you what the probability is that the random variable x takes the value m, let's say. And you have a PMF for y, which tells you that y takes the value n with some probability. And you would be interested in knowing what the probability is that x takes the value m and y takes the value n at the same time. So what's the probability of this and that? That would be given by the joint PMF. Okay. So we're going to cover joint PMFs for discrete random variables and joint PDFs for continuous random variables. So, supposing the experiment is this: we roll a fair die, we roll one random variable x as the result. We define one random variable x as the result of the roll. Okay, so x takes values 1, 2, 3, 4, 5, 6. We define another random variable y, which is +1 for an even roll, and it takes the value -1 for an odd roll of the die. Okay. So what are the possibilities for x and y listed as ordered pairs? Well, you could have 1, -1, 2, 1, 3, -1, 4, 1, 5, -1, 6, 1. Okay. What's the probability that x equals 3 and y equals 1 at the same time? Well, that's that's 0. That's not one of the allowed possible results in the sample space. What's the probability that x is equal to 3? 1, 6. What's the probability that y is equal to 1? Well, half the equally likely rolls result in. So I have. What's the probability that y is equal to 4? Well, y is not allowed to be 4, so the probability is 0. Right? Okay. Now, let's see. Now that we listed all the results, so but let's see what we can conclude. So, what's the probability of this one? 1 and -1. Right. I'm getting x is equal to 1 and y is equal to -1. What's the probability of that? Well, it's 1/6, right? The probability of getting x is equal to 2 and y equals 1. Okay, and so on and so forth. So the probability for each one of these results, each one of these outcomes, that's what you want to list in your joint PMF. Okay. So the probability that x is equal to x and y is equal to 1 is 1/6 for x is equal to 1, 3, and 5, and y is equal to -1. And it's 1/6 for x equals 2, 4, and 6, and y equals +1. And it's 0 for any other combinations of x and y. Okay, so we call this the joint probability mass function, and we write it, if we write the PMF for x as f sub x, and we write the PMF for y as f sub y, then we write the joint PMF as f sub xy, and this defines the joint PMF that we just discussed. Okay, so f sub xy is the notation that used for the joint probability distribution, the PMF, or the joint PMF for discrete random variables or the continuous random variables. Okay. in the discrete case, what do you need? Well, you need conditions which are similar to those for the single variable case. The PMF for all values should be greater than or equal to 0, right? Probabilities are greater than or equal to 0. The sum of over all the allowed values of x and y of the PMF, all the probabilities sum to 1. And what does this mean? The PMF f sub xy at x and y is the probability that x takes the value x, and at the same time y takes the value y. Okay. And if you want the probability of taking a value in a region, right, then you sum over the PMFs over all x, y, such that x comma y lies in that region in the plane. Okay. So take x and y as before. What is the probability that y is equal to 1? Okay, so that means x can be anything, and y is equal to 1. Okay, so if we go back, and y is equal to 1, so this is the sum over of f of x, y, x comma y, where this y is equal to 1, and x takes the values 2, 4, 6, and each fxy then is 1, 6. So it's 1, 6 plus 1, 6 plus 1, 6 is 3, 6 is 1/2. That makes sense, right? So this is the way you do it. Y is simply stuck at 1, and x takes values from x takes values 2, 4, and 6. I mean, when x is equal to 1, this takes the value 0. This f sub xy takes the value 0. Right, so all these terms for the other values of x would be 0. So it's 1, 6 plus 1, 6 plus 1, 6 is equal to 1/2. All right, let's try another one. There are 5 white marbles in a container. There are 8 black marbles. We're going to take 2 marbles without replacement, one at a time. Okay. So let's define 2 random variables based on the outcomes of this experiment. The random variable x takes the value 1 if the first marble drawn is white. Otherwise, it takes the value 0. The random variable y takes the value 1 if the second marble drawn is white. Otherwise, it takes the value 0. So what is f sub xy? Well, it's a probability for all of the outcomes. Okay, so what could you get? You could get 0, 0, 0, 1, 1, 0, and 1, 1. This is black, 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 white. I mean, the outcome that these correspond to are black, 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 white, white, black, and white, white. Okay, and if you get any, you can't get any other outcome, so f sub xy of xy is equal to 0 if xy is not one of the listed ordered pairs. Now, let's consider all of these. Out of the allowed results, there's 4 of them. So let's consider those. Okay, you could have taken x is equal to 0. We could have x takes the value 0 and y takes the value 0. It means you drew a black marble and then you drew a black marble. Okay, so you had 5 white and 8 black. So the probability of the first one is black is 8 out of 13. Now you've got 12 left, 5 white and 7 black. Probability of drawing a second black marble is 7 out of 12. Then the result, so f sub xy of 0, 0 equals 8 over 13 times 7 over 12. Okay. Okay, and then x equals 0 and y equals 1. Well, we already discussed x equals 0. That would be 8 out of 13. Y, 1 marble has been drawn. There are 5 white left, so 5 out of 12. So f sub x y of 0, 1 is 5 over 13 times 8 out of 12. Okay, and similarly, f sub x y of 1 y is 513 times 4 12s. Okay, and then you should be able to see that you get these results. So this is the probability for x equals 0 and y equals 0. This is for x equals 0, y equals 1. This is for x equals 1 and y equals 0. And this is for x equals 1 and y equals 1. And for anything else, you've got 0. So this is your this is your joint PMF for x and y. Okay. Let's try this one. A bin of 5 widgets is known to contain 2 that are defective. The transistors are to be tested one at a time, or the widgets, I should say. We tested one at a time until the defective ones are identified. Okay. So let's say N1 is the number of tests until the first defective is identified. N2 is the number that the second is identified. Find the joint probability for N1 and N2. Okay, so that's given to you as an exercise. And these were for a joint PMF for 2 discrete random variables. Okay, what if you had 2 continuous random variables? Okay, then you would have a joint PDF, probability distribution function. And so the function f sub xy of xy is a joint PDF for the random variables x and y. If the following 3 conditions hold, well, the joint PDF should always take values greater than or equal to 0. If you do the double integral over all x and all y, you should get 1. And the probability that the x and y lie within a region of R means you have to do the double integral over that region of the probability, the PDF. Okay. All right. So let's suppose that I have some x and y, random variables, and they're continuous random variables. And they have a joint random variable, a joint PDF, sorry, f sub xy. And f sub xy is defined this way. It takes values 3y for x being greater than 0 and less than or equal to y, and y being greater than or equal to x, and y is less than or equal to 1, and it's 0 otherwise. Now, are we sure that that's a PDF? Well, we should integrate. Okay, and get 1. So if I integrate over all x and y, well, I don't really need to integrate over all x and y. I need to integrate x from 0 to y, and I would need to integrate y from x to 1, free y. I don't have to integrate over the region where everything is 0. Okay, so that's the integral from y equals x to y equals 1 of 3y dy. So you do the inner integral first. Let's take the integral with respect to y. And then you would integrate x equals 0 to 1. This result you have to integrate in the square brackets. You have to integrate from x equals 0 to 1 of dx. Okay, so the inner integral within the square brackets, that's 3y squared evaluated at y equals x and y equals 1. And then if you integrate that with x equals 0 to x equals 1, you should get 3 halves minus 1 half, which is equal to 1. Right. Okay. Now, what's the probability that y is less than or equal to 2x? Okay, so you have to integrate over the region y over the region in the plane in which y is less than or equal to 2x. Okay, and so there's no point in integrating where the region, the PDF is giving you zeros. So we can just stick to this region given by 0 less than or equal to x less than or equal to y less than or equal to 1 with y less than or equal to 2x. Okay. And if you look here, there's a boundary at y is equal to x. There's a boundary at y is equal to 1. There's a boundary at y equals 2x. There's a boundary at x is equal to 0. Okay. So you think about the lines. You think about these lines which bound the region of the integration. And then if you integrate over that region, the PDF takes the value of 3y. Okay. Right. So if you integrate from, here's, if you do the y integral, you can integrate from y equals 2x, y, which is x is equal to y over 2, and to x is equal to y or y equals x. So that's here, x is equal to y. And the value of the PDF takes the value of 3y. So do that integration first. Do the x integral first. And then you integrate from y equals 0 to y equals 1. And if you perform the double integration, you should get 1/2. Okay. So that's an example. This is an example of how you calculate a probability using a joint PDF. You have to be able to do double integrals. If you have an issue doing double integrals, as you would do in, say, Calculus 2, then send me an email. We'll maybe have the TA do a tutorial. Okay, I'll see you next time.